Hi everyone, this video will review chemical equilibrium, but just so you know, these are the equilibria that we'll be talking about this semester. For your first exam, the focus will be on the solubility product, and we'll save these other two equilibria for a little bit later. So I like to begin equilibrium with the statement that not all reactions go to completion. Now the one I'm showing you here actually does go to completion. If we dissolve sodium chloride in water, 100% of it will dissociate into sodium ions and chloride ions. This is a reaction that does in fact go to completion. But if we try to do the same thing with barium sulfate, something different would happen. Only about 1% or so of this barium sulfate would dissociate into barium and sulfate ions in water. Instead, what you have here, as I'm sure you recognize, is an equilibrium. And I like to abbreviate equilibrium as EQ, and that's what this symbol represents. Equilibrium is a state in which the forward rate now what do I mean by the forward rate? I'm talking about the rate of this reading that you see here, the dissociation of barium sulfate into barium and sulfate. The forward rate equals the reverse rate. Now, what do I mean by the reverse rate? I'm talking about this reaction going in the reverse direction. So barium and sulfate recombining to form barium sulfate. So rather than going to completion, here is a case where we have an equilibrium. So let's see if we can define K, the equilibrium constant, and I've just chosen to use some generic reaction. You probably remember that K, the equilibrium constant, is defined as products over reactants. So you learn to write the concentration of C raised to the power of C times the concentration of D raised to the power of D over A raised to the power of A and the concentration of B raised to the power of B. And that's fine. That's really all you need to know. But actually, the equilibrium constant, what we have here in the numerator and denominator, instead of just the concentration of C, it's really a ratio. It's the concentration of C at equilibrium over the concentration of C at its standard conditions, and that's all raised to the power of C, and we would write the same thing for all of the other solutes. So here's what the expression looks like after we've written the ratios for all of the other concentrations. Again, the ratio is the concentration of the solute at equilibrium over the concentration at standard conditions. Now, just to remind you, standard conditions, you probably remember, are when gases have the concentration of 1 bar and concentrations of soluble substances are at 1 molar. So what we include in the equilibrium constant, which I'm sure you remember, is we include the concentrations of aqueous species in units of molarity and the concentrations of gases in units of bar. And when we do that, K, the equilibrium constant, is unitless. We do not include in our expressions for K solids or pure liquids. And then the last thing we'll say about the equilibrium constant is that it is temperature dependent. Most of the values that we'll be using for the equilibrium constant are only valid at 25 degrees Celsius. So let's talk about the magnitude of K. You may remember that if K is much greater than 1, that means the numerator or the products are much greater than the reactants. And another way of thinking about that is the equilibrium lies to the right. And let me just kind of sketch some generic reaction here. If K is much greater than 1, products are greater than reactants, meaning the equilibrium lies to the right. But if K is much less than 1, that means the products are less than the reactants, and the equilibrium lies to the left. This is going to be the case for acid-base equilibria and the solubility product. Values of complex formation constants are much greater than 1, so this will be the case for complex formation, which we'll talk about a little bit later. Finally, let's review some of the manipulations that we can do with K. What happens when we flip a reaction? So let me explain what I mean here. If we have A in equilibrium with B, it has some equilibrium constant, and let's say both A and B are aqueous, that we would write B over A. But if we were to flip the reaction, that would become B in equilibrium with A, and the new equilibrium constant would be A over B. And isn't that just the reciprocal of the original equilibrium constant? So if you ever see a reaction that got flipped, just take the reciprocal of K. And what about when we're adding reactions? And let me show you what I mean here. Let's say we have the reaction A plus B is in equilibrium with C, and then C is in equilibrium with D, and let's say this first reaction has an equilibrium constant K1, the second K2. If we were to add these reactions, C would cancel, and our net reaction would be A plus B is in equilibrium with D. How would we get the value of K3 using K1 and K2? Well, we would multiply those Ks. K1 times K2. So when you're adding reactions, you multiply the K values. So that was just a very brief review of equilibrium. There's more to come on the solubility product. Thanks for listening.